Millions of barrels of raw crude oil move across the open ocean every single day, carrying the raw energy required to maintain the global economy. Securing that payload requires a capital investment of up to $10 billion to build infrastructure capable of surviving 30-meter waves and Category 5 storms. Popular culture often reduces this process to the simple idea of digging a hole in the seabed to find oil. The actual engineering challenge lies entirely in managing extreme geological and hydrostatic pressure. To reach the reservoir, operators must run a continuous, zero-margin-for-error mechanical drill string up to 5,000 meters deep, crossing through heavy water currents and multiple dense rock formations. These platforms are highly volatile, closed-loop thermodynamic and fluid management systems, engineered to function in the planet's most hostile environment. Engineers use three structural typologies: fixed platforms for shallow water, floating platforms for deeper zones, and ship-like FPSOs. Fixed platforms drive steel piles into the seabed rock. Floating platforms are anchored to the bottom using massive tension leg tendons. Keeping these megastructures operational requires an isolated microcity of 200 to 500 workers running the systems 24 hours a day, 7 days a week. Because crews remain completely isolated offshore for months at a time, the facility must generate its own continuous power, while maintaining fully equipped hospitals, dining halls, and operational helipads. Operating complex pressure vessels over deep water means that human endurance and highly specialized labor are the ultimate stabilizing variables in this environment. The physical extraction process begins at the derrick, the tall tower tied a hiving reverie drill string down through the water and into the ocean floor. At the tip of this string is the drill bit, forged with tungsten carbide, designed to grind through solid rock up to 5,000 meters down. As the bit penetrates the earth, operators continuously pump a highly engineered chemical fluid mixture, called drilling mud, down the pipe. This fluid travels down the pipe, cools the bit, and flows back up to lubricate the rock. Critically, it acts as a physical weight. The heavy mud creates downward hydrostatic pressure, perfectly balancing against the immense upward pressure of the oil reservoir. Engineers monitor and adjust the exact density of this mud continuously. If the mixture becomes too light, the underground pressure forces reservoir fluids rapidly up the pipe. Deep-sea drilling relies on this continuous thermodynamic balancing act. It is a precise equilibrium between engineered fluids pushing down and the Earth's geology pushing up. If that equilibrium breaks and the upward underground pressure suddenly overwhelms the weight of the drilling mud, highly volatile hydrocarbons surge toward the surface. To defend against this, operators install the ultimate mechanical failsafe directly on the seabed, the blowout preventer, or BOP. This multi-valve structure is equipped with heavy shear rams. In an emergency, these rams are deployed to physically crush and cut right through the heavy steel drill pipe, permanently sealing the well. When this specific failsafe fails to engage, the upward surge results in a catastrophic blowout, precisely what caused the Deepwater Horizon disaster in 2010. Every operation, environmental safeguard, and human life on a multi-billion-dollar platform relies entirely on the successful deployment of this single autonomous pressure valve. Once the well is secured, extraction begins. Intense pressure often forces fluid up autonomously, but operators can deploy submersible pumps to force the liquid upward. The immediate problem is the liquid arriving on the rig is not pure crude oil. It's a volatile mixture of hydrocarbons, salt water, gas, and sand. To make the oil usable, this raw mixture is piped into the three-phase separator. Inside this horizontal drum, gravity and pressure force the turbulent mixture to stratify. Water settles at the bottom, crude oil in the middle, and gas rises to the top. The system immediately routes the byproducts away. The gas is either piped off for processing or flared, while the wastewater is chemically treated and safely discharged into the ocean or injected back into the earth. The remaining crude oil is filtered, tested for quality, and pushed forward for massive storage. An offshore platform only becomes commercially viable if it can successfully execute this continuous, high-volume phase separation directly on site. Because laying hundreds of miles of underwater pipeline isn't always practical, many operations pipe the processed crude directly into an FPSO. Spanning up to 330 meters long, these vessels serve as massive floating warehouses, capable of holding up to 2.5 million barrels of crude oil. But storing the oil introduces a new thermodynamic challenge. As the hot crude moves into the holding tanks, it begins to cool, increasing its viscosity. If the crude cools too much, it thickens into a sludge that becomes nearly impossible to pump out. To prevent this, the FPSO relies on heavily monitored, temperature-controlled internal tanks. Monitoring this requires a highly regulated process called custody transfer metering to exactly quantify the condition and volume of the stored payload. Sensors placed inside every tank continuously stream exact temperature, pressure, and fluid level data straight to a centralized control room. Measurement precision is a rigid industry mandate. A miscalculation of even a fraction of a percent across millions of barrels results in massive financial discrepancies. Every FPSO operates as an active thermodynamic containment vessel, responsible for securing and quantifying billions of dollars in liquid assets. When the FPSO nears its maximum storage capacity, a very large crude carrier, or VLCC, arrives from the open ocean to collect the payload. Maneuvering a vessel roughly 330 meters long near an active platform requires specialized marine pilots. They must instantly calculate wind speed, deep water currents, and trajectory to maintain a safe approach. They execute a high-stakes mooring process, fighting severe physics, to mechanically link two massive, independent floating structures without causing a catastrophic collision. Deck operators utilize thick steel mooring ropes weighing 100 kilograms per meter, undertaking a tense, zero-tolerance docking procedure that takes 4 to 6 hours to fully secure. Securing a rigid physical connection between two floating megastructures requires perfect synchronization against the relentless motion of the open ocean. With the two massive ships locked in position, heavy cranes deploy a wide, flexible cargo hose, creating the final physical bridge between the FPSO and the VLCC. Inside the FPSO, massive 5,000 horsepower pumps engage, pushing up to 8 million liters, or roughly 500,000 barrels of crude oil per hour through the hose and into the tanker. This violent fluid transfer demands absolute zero spark, zero flame conditions, requiring the dedicated transfer team to maintain strict operational alerts over the 24 to 48 hours it takes to load the ship. Once the carrier's tanks hit their limit, exact volume measurements are documented, custody papers are signed, and the fully loaded VLCC detaches, turning its massive hull toward global refineries. The raw material required for the plastics, fuels, and medicines of modern civilization relies entirely on this invisible, relentless cycle of deep-sea pressure management, executed by isolated crews operating at the absolute limits of mechanical endurance.